Hello and welcome back. Today we're going to be talking about electromagnetic waves, mainly for AQA A-level physics. However, as always, this is applicable to all exam boards. So we're going to be talking about electromagnetic waves. Now, this is covered in GCSE, but we go into a little bit more depth today to talk about waves. So everyone knows that light from GCSE is made up of waves, okay? And the visible part of the spectrum is just a section of electromagnetic radiation. It's just a very little bit of that, okay? And basically there's a spectrum and it goes all the way along here. You know, you can start off at 0 meters and you can go all the way to 10 to the boom, 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 like, you know, tens of meters in theory. Okay, really, probably only go up to about 1 meter, okay? But this is sort of the electromagnetic spectrum kind of thing, okay? Now, there is a key equation, C equals F lambda. This is the wave equation. This is fundamental. This will come across throughout your A-levels and alongside your GCSEs, your A-levels. Okay, so we've got C equals F lambda, where C is the speed, or now you will call it the velocity, F being your frequency, and lambda being your wavelength. So, normally, when we talk about waves, we have different types. So we have radio waves, and these have a wavelength. So we're going to do a little grid here, and these have wavelengths in meters, so this is what the square brackets mean, and they are greater than 0.1. Then we have microwaves, and these are about 0.1 to about 1 millimeter. You should have a rough idea. Infrared, you should have a rough idea of all of these values in here going all the way down the table. You should have an idea. So infrared is about 1 millimeter going to 700 nanometers, and then we move on to visible. Now this one is a must know. You must know this full stop, and that is 700 nanometers down to 400 nanometers. These are very important, so make sure you know that range. Then we have ultraviolet, which is 400 nanometers going down to about 1 nanometer. Then we have X-ray, which you will come across again very soon, which is 10 nanometers down to about 0.001 nanometer. And then we have gamma rays, which are pretty much anything less than a nanometer. So, sort of everything in this bit for sure, you definitely need to know. So these are very important. So when we think of a wave, we think of it like this, right? So this is your wave coming out. You got your peaks all along here. Obviously your troughs will be in the midpoint, okay? Now, really smart in the 1900s, Einstein came up with the idea of packets, wave packets, and he basically said that instead of being like this, where it's a whole lot, he said, what if it's just one individual wave? And we call this a photon. And a photon is literally one individual wave. It's kind of by itself. Think of it as a collection. So this is a collection of stuff, and then this is the individual. And effectively, many individuals will make the collection. That might be a nice way to think about it, correct or not. So he referred to this as a photon. And what he actually did is he used his ideas to explain this thing called the photoelectric effect, which will have its own video. Effect. Boom. And what it basically says is the energy of just one photon, so we'll just say one photon, is equal to hf, okay? And this thing called h is called the Planck constant. Now this is your first new constant during your A-levels which you're going to come across, and it has an exact value of h equals 6.63 times 10 to the power of minus 34 joules per second. A good way to check the units is make h equal to energy divided by frequency. The units of energy is joules, the units of frequency is hertz, and we know that hertz is equal to 1 over seconds, therefore it's joule seconds. So that is a nice way to think about the units for h. Now, this thing called the Planck constant you're going to come across lots. Those at university will be introduced to h bar, which is the reduced Planck constant, but that just equals that, okay? Those at A-level, you will not need to know that. So, just an example thing with a beam, okay? So basically a beam is lots of photons. So, we could say a beam could be like this. There's 1, there's 2, there's 3, there's 4, there's 5. We keep adding them, okay? And we're going to add an arbitrary amount of them. An arbitrary is just a randomly decided number, okay? And I don't know how many beams I've written there, but let's call it n, okay? So there's n photons. So the energy in this, let's do it in blue, the energy in that little bit there will be hf plus hf plus for all of the different beams. So energy actually equals nhf, assuming it's monochromatic. So it's monochromatic. So that basically means the same wavelength. Okay, so we know that energy will equal nhf, where n is just the number of photons. So that is your energy within your beam, which we've got there. Very important to know. And actually, we call it the power. So nhf is what AQA call the power. And this is because a laser beam consists of photons, so it's for a laser. So they have to be the same frequency. And the power is the energy per second, really. Is the energy per second transferred due to the photons, which is equal to nhf. So, now you know the power of a beam, which is very important to know. Therefore, this is the bit for laser power. We can do a worked example for the photon energy here. We can say that it has a wavelength equals 590 nanometers, and we want to find the energy. Okay, we know that h equals 6.63 times 10 to the minus 34 joules seconds. Okay, and we also know that c equals 3 times 10 to the power of 8 meters per second, okay? And we know that energy equals hf, and we know c equals f lambda. Here are the two important equations we need to find the energy. So, energy equals hf, and we're going to just substitute f as equal to, let's write like this, frequency as equal to c divided by lambda. So the energy is now equal to 6.63 times 10 to the minus 34. I would recommend just keeping the units in, and we'll multiply it by 3 times 10 to the power of 8 meters per second. Notice how I'm using negative powers. And we're going to divide everything by the wavelength, which was 590 nanometers, which is times 10 to the power of minus 9 meters. Now we can quite easily check here that energy unit. So the m's are going to cancel, the s's are going to cancel. Therefore, this is the only unit we have left. So energy, I believe, should be equal to 3.37 multiplied by 10 to the minus 19 joules. This is the energy within the photon of wavelength there. So, hope you guys found electromagnetic waves interesting, and I will be doing particles and antiparticles next. Have a lovely time studying.